Imagine an object so mysterious and powerful that it erases everything we know about space, time, matter, and even reality itself. It's an object that can stretch your body into a thin stream of atoms, freeze you in time, or launch you toward an unknowable point of no return. This is not science fiction. This is the terrifying, beautiful, mind-bending world of black holes. What actually happens if you fall into one? To answer that, we have to start from the beginning. Not just the beginning of black holes, but the beginning of our understanding of the universe itself. In the early 20th century, Albert Einstein revolutionized our understanding of physics with his theory of general relativity. Instead of seeing gravity as an invisible force pulling objects together, Einstein imagined the universe as a fabric space-time, which is bent and warped by mass and energy. The more mass you place on this fabric, the deeper the indentation. Planets orbit stars not because they are pulled, but because they are rolling along the curved space-time. Now imagine enough mass squeezed into a small enough volume. The curve becomes so steep that it creates a bottomless pit. It's a black hole. There are regions of distorted space-time where gravity is so strong that nothing, not even light, can escape. Black holes are not objects in the conventional sense. And this warping of space and time gets more extreme the closer you get. And what's left behind is a super-dense core that collapses into a black hole. Most black holes are born in violent stellar collapse. When a massive star, at least 20 times the mass of our sun, burns through all its fuel, it can no longer support itself against gravity. In less than a second, the core implodes. Outer layers are ejected in a supernova explosion. There are stellar mass black holes, intermediate mass black holes, and supermassive black holes, the latter sitting at the center of nearly every galaxy, including our own. That entire mass, sometimes 10, 20, or even more solar masses, is compressed into a sphere only a few kilometers across. But not all black holes are created equally. Our Milky Way's central black hole, Sagittarius A*, has a mass over 4 million times greater than the Sun, and there are even theoretical black holes like primordial black holes, thought to have formed shortly after the Big Bang, possibly with the massive mountains compressed into subatomic sizes. What makes a black hole is not just its density, but its boundary, the event horizon. This is the point around the black hole where escape becomes impossible. Crossing this threshold is like falling through a one-way door. From the outside, you seem to freeze in place, your image growing dimmer and redder until you vanish completely. But from your own perspective, you pass the horizon without feeling anything special until everything changes. The event horizon is not a physical surface, but a mathematical one, a limit in space-time, where escape velocity equals the speed of light. Inside it, even time behaves differently. Time doesn't just slow down, it becomes directional. Like a conveyor belt, it pushes everything toward the singularity at the center, with no way to resist. Let's say you hover just above the event horizon. Something strange happens. The black hole bends light so dramatically that you might see the back of your own head. This happens at the photon sphere, a spherical shell where light can orbit the black hole indefinitely. It's not stable. Any disturbance sends light spiraling inward or out. But it's real. Black holes also create gravitational lensing, bending and warping the images of background stars and galaxies into arcs and halos. In fact, this effect was one of the first indirect ways we identified black holes, by seeing how they distorted the light of other celestial bodies. You'll be stretched into a long, thin plasma stream. Now imagine you stop hovering and begin your descent into the black hole. You might float in peacefully, crossing the boundary unaware. What happens next depends on the size of the black hole. If it's a small stellar mass black hole, the tidal forces, the difference in gravity between your head and your feet, will stretch you violently. This is spaghettification. Your atoms will be ripped apart. It would be one of the most extreme and final deaths imaginable. But with supermassive black holes, the tidal forces at the event horizon are weak. It's hard to even define what going forward means anymore. Only deep inside, closer to the core, do the forces grow strong enough to tear you apart. You continue to shape the universe, even in your silence. This means you may experience more of the interior and maybe even witness the singularity. Once inside the event horizon, all directions point inward. The rules of general relativity, our best theory of gravity, simply can't handle it. There's no turning back. Any movement, in any direction only brings you closer to the center. Time and space begin to trade, roles time becomes spatial, and space becomes temporal. From your perspective, you may reach the singularity in seconds. But from the outside universe, billions or even trillions of years may pass. And while the outside can no longer see you, it can feel your presence through gravity. At the core lies the singularity, a point of infinite density and zero volume. This is where current physics falls apart, our understanding evaporates. Space and time end. Equations fail, others suggest it escapes through quantum wormholes. We don't know. It's like dividing by zero. What is the singularity? Is it a true point? A ring, in the case of rotating black holes? A bridge to another universe? We don't know. Quantum gravity, a theory that unifies quantum mechanics with general relativity, might have the answer, but we don't have that theory yet. Despite the violent processes that create them, black holes are surprisingly simple. According to the no-hair theorem, black holes have only three measurable properties: mass, spin, and electric charge. All other information, what they consumed, how they formed, when they formed, is lost. In this way, all black holes are equal. They're perfect objects in an imperfect universe. This erasure of information leads to the black hole information paradox, one of the deepest problems in modern physics. If information is lost in black holes, it challenges the laws of quantum mechanics, which say information is preserved. Some theories propose that information is somehow encoded in the Hawking radiation. Most black holes spin, and some at nearly the speed of light. These Kerr black holes don't just bend space, they drag it. This effect, known as frame dragging, forces anything near the black hole to rotate with it. There's a region around spinning black holes called the ergosphere where nothing can remain still. Even light is forced to move. If you're clever, you could use the ergosphere to extract energy from the black hole, a process known as the Penrose process. Some theories even propose that advanced civilizations could use black holes as power sources or even wormholes for travel. You might think black holes are eternal, but Stephen Hawking proved otherwise. Through a quantum process near the event horizon, black holes can emit tiny amounts of radiation. Over immense timescales, this Hawking radiation causes them to slowly lose mass and energy. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate. Supermassive black holes could survive for 10 to the power of 100 years or longer. That's longer than the age of the universe by many, many orders of magnitude. Even after galaxies fade and stars go dark, black holes will remain cosmic tombstones marking the final stages of everything. Black holes don't just challenge physics, they challenge philosophy. What does it mean to exist when you're cut off from the universe? Does time mean anything near a singularity? Are black holes gateways to other universes? Do they lead to the birth of new universes in a multiverse structure? And perhaps most importantly, if we can never observe what's inside, will we ever truly know? Black holes are the ultimate reminder that the universe is bigger, stranger, and more mysterious than we can imagine. So what happens if you fall into a black hole? Your body is destroyed. Your timeline is severed. Your connection to the universe is lost. But your story becomes part of something larger. An unsolved puzzle, a gravitational ghost, a mystery embedded in spacetime. Black holes consume, but they also inspire. In their silence, they challenge us to understand the impossible. And in doing so, they bring us one step closer to understanding the universe itself.